Hi friends, so we are onto our course on risk conscious operations management for complex engineering systems, and this is third module entitled risk based engineering. I think we had discussed initially that this risk conscious operation management it is based on one of the subject that I have developed is called risk based engineering. So becomes essential to discuss at least the salient feature of the risk based engineering. If you want to go in details of risk based engineering, definitely you can refer my book it published by Springer. But now we will be talking about introduction on this subject, that is risk based engineering. And this is a NPTEL course, and I am CEO ERAM Engineering Risk Assessment and Management Center, Mumbai, India, and I am also faculty at Luleå Technology University, LTU, Sweden. So let us get on to the introduction component of this week. So this is basically an outline. First lecture will be on introduction, and then risk based engineering framework, and then deterministic and safety assessment. In fact, to be very precise, the role of deterministic safety assessment and probabilistic safety assessment in risk conscious operations management through risk based engineering. And there are some special areas that need attention because we are talking about the operation and maintenance ecosystem. Since risk is central to this subject, let us spend a minute on this mathematical formulation of risk. Risk is nothing but a product of likelihood and consequences. That means any undesirable event, it's a likelihood. That means how frequently it occurs and what consequences are associated when this event occurs. Let's say, for example, in our house, we have power failure conditions. So, how frequently this power failure occurs in our house, and or rather say even for the societal application also. So, what is the likelihood and what are the consequences? We know that once power supply is not there in our house, we have to make arrangement for having some alternate source of light, because without light we might meet into the accident. It could be sleeping or hitting some object and falling down, and then missing our valuable time, whatever we want to do. So what are the consequences? Any of these things could be consequences. If we talk on transport scenario, power supply failure has definitely led to the accidents. And how frequently it happens on road conditions, and then what are the consequences if we demarcate some region that becomes our system. We find out in that area what are the frequency and what are the consequences. So we will find that there are the frequencies 1 or 2 power failure events on this particular area, and the consequences are 1 or 2 or n number of people meeting with the accident, and sometimes injury or sometimes fatalities, loss of life, it occurs. So this is a statement complete in itself. And when we want to do for a complex engineering system, there are n number of scenarios. So I is equal to 1 to n, and for each scenario what is the likelihood and what are the consequences, and product of this will give us the net risk from a particular complex engineering system. So with this background and introduction for this week, let us move to the introduction and background for risk based engineering, because it provides the fundamental basis for risk conscious operation management. So we can also say ORCOM is one of the spin-off of risk based engineering, because the risk-based engineering as a subject was applicable to design, operation, maintenance, emergency condition. I mean, in plant also we can have operating plant also we can have emergency condition. But then it is now what we will be discussing in this in this course is application of RBE, that is risk-based engineering to risk-conscious operation management. And for that we must understand what is operation management ecosystem. So in this lecture we will be discussing this, and then comparison with the traditional approaches. Since 5, 6 or 7 decades, there have been some or maybe more than that, some procedures or some approaches are there. One of them is deterministic. We will be discussing this approach in this lecture itself. And then probabilistic approach. So probabilistic approach, when many elements like reliability, availability, maintainability and safety, they are joined together, then it is called RAMS traditionally, and it is finding application in many areas because it tries to address the throughput of the company or a system, and also it talks about safety on the other hand. Then dependability is further with few more elements. It is derived from essentially from RAMS only, and I think we have covered last lecture on dependability thoroughly, because we find application is risk conscious operation management. What are the dependable system, dependable resources, dependable environment that makes the risk conscious approach for operations management. And then probabilistic risk assessment. We saw that in RAMS also there is a component called safety, but let us accept this fact. Safety is basically a qualitative parameter. Okay, it can be a target, but when we want to talk about a scientific approach to safety reduction or addressing certain areas which require special attention, then we have to have a mathematical tool or analytical tool, and that probabilistic risk assessment provides an elegant platform to have that. And as such, in complex engineering parlance, safety is referred as overriding factor. That means safety should be given importance in support of any decision, and then later on only other factors like plant operation or throughput and all, they come into picture. So PRA becomes a very powerful tool wherein it addresses the risk and addresses safety through risk reduction or risk assessment, and then it talks about what are the consequences of unreliability, unavailability and all that. So in one matrix, that is risk, other areas are also, and nowadays we are talking about security also. So for security also, there are efforts going on world over to have an approach called probabilistic security risk assessment. And in my last but one lecture, I will be discussing that part also, because I feel for plant nowadays safety is because of random failures and all that. But the security, it enters through very informed and you can say deliberate attempts. So that needs special attention, and that's how we have one week or module on security risk assessment also. And consequences of probabilistic risk assessment or security risk assessment is risk informed and risk based engineering. And so risk informed we can see it in a regulatory parlance, when the projects are reviewed and then some decision has to be made in a real time system. So whether we can move away, and if we can move away from our stipulated technical specification requirement, what are the options that are available. So risk informed has become a very popular approach, and risk based approach also for like in service inspection, and there are many systems where it is used for use when other options are not available, or we want to support the other alternate options. So that is what we have the complete background and introduction for this subject. And then let us say if we have to discuss explicitly why risk based engineering for ORCOM. So first reason, of course, we have discussed that risk is the fundamental matrix in operation maintenance and decision making. Why? Because risk is a overriding factor. Okay. So, and then in plant we have this one document called technical specification. Let us we can call it as a safety technical specification, and that those specifications are provide stipulation and conditions for plant operation, and these conditions need not be violated or bypassed. If any bypassing or violation happens, then the plant has to approach the independent body called regulatory, and from there we have to bring clearance. So, for further operation or from some waiver, or it depends what is the situation. So, that is why safety is the overriding factor. And then why risk conscious operation management? One is it comes because of risk centered development. And second thing is human factor has been a major contributing factor to one of the major contributing factor to the accidents. Our major accidents, if you see the historical records, will find there are many events. It doesn't mean that human is a sort of a problem or a challenge in operation. No, it's a human who have kept the risk level so low. That's why we are having like for nuclear system, they are addressed as having the best safety records, and then why they have it? Because it is the best quality of human through training and program and we have implemented. So that is why it is less. But then when we can see everywhere, right from conceptualization, design, operation, maintenance, aging management, when everywhere human is involved, the human element will be seen, because it is at the root of any venture, any analysis, any development, design we do. And then operating ecosystem, typically you will see that it is a human action intensive ecosystem. So, the lot of interactions happen, though the safety ensures that humans cognitive load doesn't increase, and then plant in fact during emergency conditions for half an hour human intervention is not required. So these kind of provisions are also given. Sometimes some passive systems are designed where human interaction can be reduced. So everywhere efforts are there so that this particular aspect, that is human factor, can be addressed. Then goals and criteria. PRA and RBE. In fact, PRA provides some goals and criteria like unsafe state of the system or plant damage states, the frequency, and then risk-based engineering takes it further in line with what we have, this best estimate, which is a deterministic concept, and then it says 95% of the bound should be used, and you can go further also depending on what was the coverage of our analysis. And then operation ecosystem is characterized by natural language communication. Okay. It will be good, very good, excellent, performance is good, excellent. The quantification comes later on performance. That comes through systematic risk and reliability analysis. And sense of component failure. If I say the failure probability is 2 into 10 to the minus 3, what it means on ground, whether it is for a component, for it is a safety system, for a and whether it is a probability or it is a frequency, all these things should get translated to the natural language, or natural language should come forward for the interpretation of like we say beyond design basis accident, the frequency should be 10 to the minus 6 per year. Now this has been reflecting in many technical guides and all. So there should the gap between natural language and quantified estimate should be reduced, and that is called risk communication, and it occupies a very good big dimension. So the third bullet in the is we should understand what we are meaning by 1 into 10 to the minus 6 per year. Like I said, in a particular let us say transport system, the failure frequency likelihood is 1.5 per year. Now, if I compare that with for a system like nuclear, where frequencies are touching 1 into 10 to the minus 6 per year. So, so communication gap will reduce if we convince people by comparing with various systems. So, what we mean by 10 to the minus 6 and all. So, this is very important. So, risk conscious operation management requires an approach wherein risk is centered and human factor is addressed and communication models are available, so that in fact it can be used for public communication also. And the second part of this is whenever we give statement 2 into 10 to the minus 6 per year, if I say, but then for every statement when we set quantitative, so like there was a problem with the natural language, there is a problem with the quantified metrics also. Now there are so many conditions under which the analysis was done and the results were done. So that means first we have to talk about what is the scope of the analysis. The scope of an analysis, if it is only at the limited scope or only at level 1 risk assessment level, then probably we can say, but then we are not talking about level 2 and level 3 also. So we have to talk about, we have to give a background that it is not level 1, it is basically plant damage state. It is not the risk level from the plant, because risk level is when the radiation reaches the public domain. And level 2 is basically when the hazard crosses the containment. Okay. So analysis, constraint and assumption. What assumptions have been made? So scope and constraints which are there for the analysis, that, like for example, if I analyze a digital system, in digital system software is a component where even now there is no consensus what should be the probability or how it should be evaluated. People are using with certain methods and all that, but if you compare with hardware system, the software system, so and software is a integral component of the digital systems. So these are the issue, and then we have to give a background of how we have compensated these kind of constraints. Now let us come to the definition of risk-based engineering. What we mean by this. So risk-based engineering is a scientific and technical approach oriented towards risk postulation, assessment in support of design, operation, maintenance and even life extension activities. And their management is one component and decision making is one. Of course, decision making is also a part of the management. So it is basically for plant management or regulatory ecosystem, whatever. So here we are not going into the probabilistic or deterministic. The idea is these two techniques together, they provide the holistic approach. So that's why a risk-based approach. And since risk-based engineering is a fundamental subject, risk-conscious operation management is a spin-off of risk-based engineering. And then how this definition or the objective is realized, integration of deterministic and probabilistic, as I said. And there is no distinction between both are participating for holistic and integrated solution. And development of monitoring and surveillance in ORCOM. See, then when we talk about risk-conscious operation management, the ecosystem require a very strong framework for surveillance and monitoring, because control room is the central place where all the activities are monitored and governed and managed. So, and it is 24/7. I'll come to when I define the risk-conscious operation management ecosystem, and complies to qualitative metrics like risk and performance. Okay. So these are the derivatives from risk-based engineering, which it enables in respect of reliability, availability, maintainability, safety. Safety means we are talking about risk, and through this risk matrix we are trying to address the full RAMS paradigm. Okay. So what are the major elements? We already discussed that it's a complex system, and randomness is inherent part of. So if we do not consider the probabilistic approach, the approach will not be holistic. So that's why the deterministic and probabilistic complement each other, and then we have an integrated statement of risk and the risk matrix is arrived, and that becomes the driving the force for managing activities in operations. Since operation ecosystem is a human, so human factor for takes the central place other than the common cause failure in risk based engineering, and that's how it enters into risk conscious operation management. Now, risk conscious operation management, risk based engineering provides a transfer function that is called risk conscious transfer function, and that is how risk conscious operation management we have. And here I'll point out that there is a discussion in risk conscious operation management about risk conscious culture. So, risk conscious culture also comes into the play, and that's how we have an operational ecosystem through risk conscious operation management. Okay. Now, additional scope, what we can call that this risk based engineering, mainly it is adoption of extension to design and operation. So, here the design we have not touched upon, only we are talking about the operational component of extension of risk based engineering. Then any activities through risk conscious operation management, and where the framework is risk based engineering, the first step will be to have a very consolidated and sound definition for what we want to do, because the risk management is nothing but changing the policy or updating the policy or looking for some solution or looking for some arguments for regulatory approval. So, we should have a very clear cut definition of what we want to do and what are the resources that are available to us. And essence of operation is nothing but 24/7 monitoring, surveillance, maintenance management. Maintenance management is one of the major activity from volume wise, activity wise, and manpower resource wise, and of course inventory wise also. So, it is an integral part of operation, and then this is required for oversight, regulatory oversight, and because any operation system, if it is founded on this very scientific basis or technical basis, then it will have an independent regulator. This is a very important point. If there is no peer review or independent regulator, then there is a chance of missing on certain aspect, and it cannot be called as a professional system. And regulatory framework is required. So, as I said, whatever is the definition of our problem, we have to say, we have to prove and get approval from the regulators for whatever change that we are stipulating, and this risk conscious operation management is all we are getting from there. Now, as I said, human factor consideration, yes, it is an ongoing process in operation ecosystem, and the traditional approach to keep a quality of manpower resource is by training and qualification. Okay. So, rigorous training, then before we pass all the exams, there is a walk down. So, after passing the written and this examination, we have to go for a walk down and then interview, and then a administrative authorization. So, that's how a person gets qualified. So, the trainee has gone through the different levels for enhancing its knowledge of the plant processes, and then finally he is qualified to a operational system. And design and operation aids, there is a continuous process in the control room of the plant, how design document can be updated periodically, how they are designed, and how operation documents and aids. There are many aids are provided to operations, right from, we can say, some documents that need to be referred, some office order on administrative basis, to certain decision making jobs, like what affects operation, what doesn't affect operation, prioritization and all these things, and then some advisory tool also are provided, and assessment of, and then in spite of doing all these things, then a continuous assessment of human factor in the plant is an integral part of this thing. So state of the art, and finally where state of the art is there in terms of improving the training ecosystem, risk monitor to support the operation and maintenance. Most of the or many plants in world over, nuclear power plant, they have a risk monitor. That means if I want to do something, I will see is there any reduction in increase in risk or there is no increase in risk. So so we do at component level, system level and at plant level. Then plant simulator, they have become integral part of any operation ecosystem, because it has been realized that plant simulator provide an effective mechanism for teaching, learning and grasping the concepts of the plant. Then AI, artificial intelligence and machine learning approaches for developing operator support system, especially for emergency condition. And then human prognostics. There is a element of that, periodic medical checks and all they are there in the operation, but then systematically and they are I think periodic and all, but then further improvements are required to keep human prognostics in point, and whether it is a physiological component or psychological component, they should be kept under the check. And then the most important, root cause analysis. Root cause analysis, because we are talking about the failure, so any failure or especially serious failure, they should go through the root cause analysis and fundamental causes should be understood and they should be eliminated. And follow-up action will only tell how good were they are in getting the root cause of the failure. And then risk characterization. Since we are talking about the risk characterization becomes the central objective. And how we do, in first slide we saw what is risk, how risk can be mathematically expressed. And now here we have, so risk is having two components. So let us say, first of all we have to see absolute goals. That means suppose if there are set goals given by regulator, so we should not be falling or faltering on those goals. We should try to achieve those goals. Then second thing is, if there is any change is being reflected or a particular like maintenance or in-service inspection are being incorporated or into the plant, then what we can do is we can develop a risk matrix. So how in that there are two things, that is likelihood, as I mentioned, and consequences. And then it will show us the areas where there is no freedom, the areas where little freedom is available and we can take decision, and then this is further safer, and these are the safest area require minimum intervention actually. So these are the risk metrics that are allowed, and this comes from where? We should have a risk model of the plant. That means probabilistic risk assessment model. Even if we have a level 1 model where we do system analysis, it is sufficient. And what? The results should capture the uncertainty. That means any quantified estimate should capture the uncertainty, upper bound, lower bound, and that should lead to sensitivity analysis. So these things what I am talking about, they become part of the safety or risk conscious culture. The subjective component is integral to the, as I mentioned, the qualitative language or the, so they become, critical in plant operations ecosystem. So the subjectivity which comes with the even quantitative estimates or the subjectivity which comes with our expression, that should be crisp, in a crisp way should be brought about, and then this matrix is available for any change actually. Okay, so in this lecture we saw introduction of RBE, how it is able to have one spin-off called operations, and that's how it manifests risk conscious operation management. And then RBE framework we have discussed the role of deterministic and probabilistic approach. Risk characterization, wherein we realize that subjectivity should be, for any result, subjectivity should be brought out explicitly. And then assessment and adequacy of application, there should be a sort of not only root cause analysis, then followed by deliberations, and what was left out, accounting for that, whether we have provision in the plant to account for those uncertainties. So like that discussion. So this was a introduction to the course on risk-based engineering, which is an input for risk conscious operation management.